I'm Gianna. I'm a grad student in the Thompson lab. Our lab studies Huntington's disease. Huntington's disease is a neurodegenerative disorder. It starts at around middle age, and it can cause really bad, uncontrollable movements. And it's ultimately fatal. This disorder can devastate some families because if one of your parents has it, you have a 50% chance of getting it. The reason for that is because Huntington is a gene that is mutated that causes the disease directly. So it's just one gene that's responsible for all of this. And the mutation that causes it is an expansion. Normally, Huntington does a really important function in cells. It helps take out the cellular trash and clean the cell up. But when Huntington is expanded, it can't do that function, and instead it aggregates into these big accumulations that are toxic to cells. So there's a lot of interest in trying to figure out how we can clear those aggregates and allow the cell to continue performing its normal functions. One modification that can help Huntington be cleared is phosphorylation. So you take a phosphoryl group, stick it on the protein. That can tell the cell a lot of different things like, oh, this protein needs to be degraded or it needs to go do a different function. And so we know that Huntington gets phosphorylated. Specifically, it gets phosphorylated at a residue called serine 13. So we know that serine 13 phosphorylation occurs, and we also know that serine 13 phosphorylation can help Huntington get broken down in a cell, which is what we want to help with Huntington's disease. So my lab has looked in recent years into what is the cellular machine that produces that phosphorylation. What is the kinase? A kinase is a phosphorylation enzyme that sticks the phosphoryl group specifically onto serine 13. And we know what that enzyme is in cell culture. We know that it's Ikkb, the NF-kappa B kinase. However, we don't know what kinase it is in brains. And you can imagine that in cell culture, which is an in vitro system, it might be really different from in an animal model or in a human. So we created an animal model that is a cross of an IKK knockout with a Huntington's disease expanded, mutated mouse model. And we found that in that crossed mouse, phosphoserine 13 Huntington is reduced and symptoms are worse, suggesting that IKK really is necessary for that phosphorylation of Huntington. This could lead to potential therapeutic targets in the IKK cascade that could really help people with Huntington's disease.